Hello friends, welcome to supplementary video lecture series. Today's topic is analysis of continuous beam using slope deflection method. Based on your suggestions and feedback received, I am overwhelmed with your responses, and that's why based on your suggestion, it is a few students have suggested to make a video on the slope deflection method. So here I remind you that the aim of this video lecture is nothing but it's a supplementary video lecture. That means it is additional resources beyond the classroom at any time, anywhere, as per your convenience. You can solve your doubt by watching this video. So in this video, we are going to discuss about the basic of slope deflection method and one of the practice example. So let's start with the example of it. So basically, slope deflection method is one of the fundamental classical method to analyze the continuous beam, rigid frames. It is including the support settlement and support deflections, support rotations problem, and sway problem. Sway, that is a nothing but that's a lateral deflection. As of now, we have not discussed about the sway in the case of the frame, but later on we will discuss about the sway problem and how it is going to apply the slope deflection method that we are going to see. So this is one of the basic fundamental method like a moment distribution method, and it gives the strong foundation for the upcoming method of the our topic, that is the stiffness method. So let's start with the practice example of the slope deflection method. So here it is a two-span continuous beam. You look this data is a familiar because you can see in the another video the same data, same example we have solved with the moment distribution method. So here you have a chance to compare both the examples from both videos and using both different methods, and what is the difference in the calculation and what is the difference in the answers that you can compare it. So let's start with the solution here. First step, to determine Ki. As it is a displacement method, here primary unknowns are displacements or rotations. So what is the Ki for this? At the fixed end, it is a 0. At B, there will be 2 Ki. One is a horizontal displacement and one rotation. Similarly, at a C, one horizontal displacement and one rotation. But as you know that we are neglecting the axial deformation. So basically there are 2 Ki's remaining. There is a 2 rotations. There is a 2 theta B and theta C, rotation at B and C, which is our unknowns. So first we have to identify that what is our unknown. As it is a displacement method, our unknown will be primary unknowns are the rotations or displacement. Let's move to the second step, that is a friction moments. So friction moments equation, you all are very good in remembering this friction moment. Now we have to apply this friction moment over this problem. So here for the span AB, it is a eccentric point load 50 kilonewton. So what is a friction moment? At the left hand side, it is anti-clockwise movement. Right side, it's a clockwise. So as per our sign convention, we are considering clockwise movement as a positive, anti-clockwise negative. And what is the equation? Minus WAB square by L square. If we are applying the value, we will get the minus 24 kilonewton meter on the left hand side and 36 kilonewton meter on right hand side. Similarly, for the MFBC, MFCB, so answer will be minus 62.5 and 62.5. So this is the fixed moment, and which we have applied in the fixed beam cases also. So similar way, we have to find out the fixed moment over here. Next step, that is a slope deflection equations. So basically there is a one fundamental equation you have to remember. There is a MAB equal to MFAB plus 2EA by L, 2 theta A plus theta B minus 3 delta by L. How this equation is derived, that we have seen in the class, but basically it is a combination of all the parameters. It's a friction moment due to the loading, rotation at support, settlement of the support, and by doing the combination, it's this equation was derived. Now here in this case, MFAB was minus 24. I, if you see in the previous, as per the given data, I is a nothing but taken as a 2I. L, that is a 5, and theta A is a 0 because there is no rotation of the support is given, as well as the support is a fixed, so there will be no rotation in that. So theta A is a 0. There is no support settlement, so delta is also 0, so remaining is a theta B. So the first equation of the MAB, that is a minus 24 plus 0.8 EI theta B. Similarly, second equation, MBA, that is equal to MFBA plus 2EI by L to theta A plus 2 theta B. A and B will be going to interchange as compared to the first equation. So here the equation will be become 36 plus 1.6 EI theta B. Similarly, if we talk about the third equation, MBC equal to MFBC plus 2EI by L, 2 theta B plus theta C minus 3 delta by L. Now in this case, theta B and theta C both are unknown, so we have to keep EI theta B theta C as a unknown only. So the third equation is a minus 62.5 plus zero point 0.8 EI theta B plus zero point 0.4 EI theta C. And last one, in that we have to just interchange the coefficient of the EI theta B and theta C, and we have to change the friction moment. So MFCB is a 62.5. So the equation will be 62.5 plus zero point 0.4 EI theta B plus zero point 0.8 EI theta C. So these are our slope deflection equation. If it is a one span, there will be two set of the equations. So we have two spans, so total four equations we have generated. Now next step is a equilibrium equations. Equilibrium equations are with respect to our unknowns. So we have a two unknown. So as first unknown is a theta B, that is a rotation at B. So with respect to rotation, we have to do the summation of the moment at that joint. So how many members are connected at the joint B? There is a BA and BC. So summation of the moment of the total moment of the joint B, that is equal to 0. So what we can say that equation is to become a MBA plus MBC equal to 0. Whatever equations we have generated for the slope deflection equation from the previous step, that we have to put it over here. So both equation we are putting over here, and we will make it as a generalized one equation by adding the coefficient. So it is a 2.4 EI theta B plus 0.4 EI theta C equal to 26.5. Similarly, second unknown is theta C. With respect to theta C, we have to consider total summation of the moment at the joint C equal to 0. As it is an end support, only one member is connecting, that is a CB. So MCB equal to 0. And we have to put that equation over here. So the final equation for the second one is a 0.4 EI theta B plus 0.8 EI theta C equal to minus 62.5. So basically here you can see that we have a two unknowns. So we have a two equilibrium equations, and based on that we are generating two linear equation to find out two primary unknowns. So based on the solution of this equation, what we can get that EI theta B is nothing but 26.25 by EI, and theta C is a minus 91.25 by EI. What is the indication of the plus and minus sign? Plus is indicating clockwise rotation and minus is indicating the anti-clockwise rotation. So here we suppose if we know the value of the EI, so if we put in this, so for example, let's say if we have a value of the 16,000 kilonewton meter square. Okay, so if we are just putting the 16,000 in this equation, so we'll get the 0.0017 radian amount of the rotation at the B. Or if you are converting to degree, so it will be get 0.09 degree. So that means here, along with the final shear force and bending moment, we can find out the rotations, and which will be give some idealistic behavior of the beam. So how it is going to, we can see, we can visualize it. Let's see this diagram. So it will be show the deflected shape of the beam, and you can see over here between the span BC somewhere the maximum deflection, this white line whatever you can see, that is nothing but it's a deflected shape of the beam. So if we draw the tangent to the deflected shape, so it will be give the slope of the both the point. So you can see here first a white line over here as compared to the actual reference line, it is going clockwise direction. So here the rotation is a 26.25 by EI, there is a clockwise rotation. While if you consider this one, so there is a minus which will be indicating the anti-clockwise rotation at the joint C. So the advantage of this method that along with the moments we can find out the basically the displacement of rotation at the respective locations using this method. Now let's move to the next point, and whatever unknowns we are getting, that we have to put in our actual equations MAB. So if you put the value of the EI theta B in that, we will get the first moment, that is the final moment MAB equal to minus 3. Similarly, second equation, so MBA will be 78 kilonewton meter, MBC will be minus 78 kilonewton meter, and MCB will be 0. So here two things you have to notice, that whatever equilibrium conditions we have put it, MCB equal to 0, so that is a satisfied. MBA plus MBC equal to 0, that is a satisfied, because this unknowns we have find out from that equation only. And you can compare these answers with bending moment distribution method. In that also we are doing the end correction first, so MCB is a 0 in that case also, and we are at the end whatever summation we are doing, so moment at BA and BC will be equal and opposite sign. So there is a way we can cross check the answer. Now based on the sign we can put the moment in the our actual beam. So here -3, that is indicating anti-clockwise direction, 78 clockwise, -78 anti-clockwise, and 0, that's a 0. So based on these moments, we have to find out the support reaction of this beam. How to find out? Separate these two beam, and we have to find out the only for the AB. So what we consider the moment, take a moment about A, and it's a minus VB into 5 plus 78. Both are VB into 5, that is a anti-clockwise moment, 78 is a clockwise. -3, there is anti-clockwise, plus 50 into 3, we are taking moment about A. So we will get the VB1. Why it is a VB1? Because VB is a supporting to the BAB and BC, both the members. So it is a divided into two portions, VB1 and VB2. So total load is a 50. So VA will be become a 5 kilonewton. Similarly, we have to find out the support reaction for the BC. We will take the moment about B. So what we will get? Minus VC into 5, minus 78 plus 30 into 5 into 2.5. So we'll get the BC equal to 59.4. Total load is a 30 into 5. So 150 minus 59.4, that is a VB to 90.6. So if we do the summation of the VB1 and VB2, so we can get the total reaction VB. So here that is a 135.6. Based on this, we have to draw the shear force diagram. So first it is a 5 kilonewton upward at the A, then A to D, there is a constant, then it is a minus 50, so 5 minus 50, it's a minus 45, then it is again constant, and going up at the support B plus 135.6, it is a 90.6, and then it is a UDL of the 30 into 5, so minus 59.4, and reaction at the C is a plus 59.4, so it's a 0. So that's a shear force diagram. Uh, at which point the shear force is 0? At that point, we will get the maximum bending moment. So you can use the similar triangle, or there is another short methods are there. You can find out that point, and that is a 1.98 meter. And with respect to that, there are two ways of the drawing the bending moment diagram. So first way that we can show the based on the net diagram. Here first moment is a 3. Then at each and every location we have to find out the moment, and we have to draw the bending moment diagram like we are drawing for the one span. But as we have discussed earlier also in the lectures, that in the continuous beam there is an alternative way to draw the bending moment diagram to show the support moment and span moment separately. So how to draw it? So let's see. Here all the moments are hogging only. So all the moment at the support, it will be negative. So that we will show at the above the line, and we will connect the lines. So this is a diagram because of the support moment. Along with that, if we draw the span moment, so there is a first span, that is a 50 kilonewton. So maximum moment in the span, that is a WAB by L. So that is a 60. And in the second span, it is a UDL. So it is a WL square by 8. So it's a 93.75. So here either you can draw in this manner or in this manner, it's the same thing, because if you are comparing this diagram, so here total 60 is a positive moment. If you find out the component of this negative moment over here, so you can consider any value, and if you deduct from the 60, so you will get the automatic the net moment is a 12. Similarly, you can find out the maximum moment at some location at the 1.98 meter. So this is a way you can draw the bending moment diagram. Either you can draw the net diagram or overlapping diagram of the support moment and span moment. So with this, we are ending this example. So here the final, before end this, the one kind of the review question, it is a depend on your perspective. You can share your answer, your doubts in the comment section. And question is that which method should be used for the structure analysis? as per your perspective. You can see both the videos, same example, slope deflection method, moment distribution method, which method you are feel more easier and why. So only the name of the method is not sufficient. You have to write the reason along with that. So I am expecting your answers in the comment section. Anytime, if you have any suggestions, feedback, or any doubt, you may share with us. Thank you so much. Take care. Bye bye.